This perfect ring, 1.3 billion light-years in diameter and 4 billion light-years in circumference, is one of the largest known structures in the observable universe. But here's the problem. According to our current theories of the universe, it can no longer contain it. Theoretical calculations tell us that in the 13.8 billion years of cosmic history, a structure with a maximum diameter of 1.2 billion light-years could only have formed. This ring is a full 100 million light-years larger. It's like a conspicuous bump suddenly appearing on a smooth surface. How did it form? Are all our measurements of the universe wrong? Today, we'll start with this bump to remeasure the size of the universe. In the 1st century AD, Ptolemy claimed the Earth was the center of the universe. In the 16th century, Copernicus asserted the Sun was the center. His supporter Bruno was even burned at the stake in Rome's Campo de Fiori for this claim. But what truly changed everything was measurement. In 1677, Halley, the man behind Halley's Comet, conceived of using the transit of Venus to measure the distance between the Earth and the Sun. He predicted 2 consecutive transits in 1761 and 1769, but sadly, he didn't live to see them. He left behind dozens of observation points, like a will, for posterity. In 1769, Captain Cook, on a voyage to Tahiti, successfully recorded Venus' passage across the Sun, despite interference from warships and with special permission from the British Navy. Ultimately, the French mathematician Lalande calculated that the distance from the Earth to the Sun is approximately 153 million kilometers, or 1 astronomical unit, AU. The diameter of the solar system is approximately 60 Australian dollars, 9 billion kilometers. But what about the Milky Way? In 1838, Bessel introduced a new unit, the light year. 1 light year is approximately 9.5 trillion kilometers. He measured Cygnus 61 to be 10.3 light-years away. However, the Milky Way is so vast that even a light year isn't enough. William Herschel used the stellar counting method to draw the shape of the Milky Way. He placed the Sun at the center. Until the early 20th century, Harvard Observatory astronomer Leavitt discovered the measuring stick, Cepheid variable stars. There's a fixed relationship between the period of their brightness variation and their true brightness. By measuring the period, one can know how bright it is and thus calculate the distance. In 1914, Shapley used Cepheid variable stars to measure 69 globular clusters, and 4 years later concluded that the Milky Way's diameter is 300,000 light-years, and that the Sun isn't at the center at all, but rather in the suburbs. This conclusion was so revolutionary that in 1920, the famous Shapley-Curtis debate erupted in the astronomical community. Is the Milky Way the entire universe, or just an island in it? Neither side convinced the other. Then, in 1924, a young man named Edwin Hubble appeared. He found Cepheid variable stars in the Andromeda Nebula and calculated that they were millions of light-years away, far beyond the boundary of the Milky Way. Andromeda wasn't a nebula, it was another galaxy. Suddenly, the universe seemed infinitely larger. Hubble didn't stop. In 1929, he measured 24 galaxies and found that they were all moving away from us, and the farther away they were, the faster they were moving. This is Hubble's law, the first direct evidence of the expanding universe. Einstein initially refused to believe it, but in 1931 he went to the Mount Wilson Observatory himself, and after seeing the data, he had to admit he was wrong. Since the universe is expanding, then working backward, it must have once been an infinitely dense point. This is the Big Bang Theory. The discovery of the cosmic microwave background radiation in 1964 made this theory mainstream. Currently, it is generally accepted that the universe was born 13.8 billion years ago. But soon, a star proved everyone wrong. Designated HD 140283, about 200 light-years from Earth, it belongs to the second generation of stars, almost entirely devoid of metal, meaning it is extremely ancient. NASA named it Methuselah after the longest living figure in the Bible. Initial calculations estimated its age at 14 to 16 billion years. Older than the universe? That's impossible. Either the Big Bang Theory is wrong, or the age calculation is incorrect. Later, scientists repeatedly revised their calculations. 14.4 billion years in 2013, 13.7 billion years in 2018, and the latest result in 2025 is 14.2 billion years. It consistently hovers on the edge of the universe's age. Meanwhile, the National Astronomical Observatory of Japan discovered a gas cloud called Bacmea 13 billion light-years away, with a diameter of 55,000 light-years and a mass 40 billion times that of the Sun. According to current theories, such a large structure shouldn't have existed in the early universe. These contradictions point to a possibility. Our understanding of the universe's expansion rate may simply be wrong. If the rate of expansion is wrong, then the 13.8 billion-year age of the universe may not be the correct answer. So, how did the universe begin? According to the Big Bang model, 13.8 billion years ago, in some unknown place, a tiny sphere, only about 1 centimeter in diameter, suddenly appeared. It contained no matter, only energy, with a temperature of 1.4 times 10 superscript 3 superscript 2 degrees Celsius. How fast did it expand? In 10 superscript 3 superscript 2 seconds, it went from 0 to 1 centimeter, a speed 10 trillion times the speed of light. This extremely brief period of superluminal expansion is called inflation. Inflation explains why the universe today appears so uniformly flat in all directions. After inflation ended, expansion slowed, and the temperature decreased. In a fraction of a second after the universe's birth, energy began to condense into fundamental particles such as quarks, electrons, and photons, and the 4 fundamental forces emerged. Interestingly, particles and antiparticles were created and annihilated in pairs. But for some reason, there was a tiny excess of matter. This tiny amount constitutes all our galaxies, stars, planets, and even ourselves today. In the first second, the universe's diameter was already 400 million kilometers. In the first minute, its diameter reached 1 light-year. But at this time, the universe was still completely dark, because electrons acted as a barrier, blocking all photons. Until 380,000 years later, the temperature dropped to about 3,000 degrees Celsius, and for the first time, atomic nuclei captured electrons, finally releasing photons. This was the first flash of the universe. The cosmic microwave background radiation we observe today is the afterglow of that flash. Afterward, the universe fell into darkness again, and millions of years later, the first star lit up in the fog. Those first-generation stars had long since exploded and died. The heavy elements they ejected gave birth to second- and third-generation stars. Our Sun is a third-generation star. Methuselah star belongs to the second generation, carrying the ashes of first-generation stars. But the question is, if even Methuselah star's age may exceed that of the universe, where did the first-generation stars come from? Regardless of how these mysteries are ultimately solved, one thing is certain: the universe will die. In 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, merging into the Andromeda Galaxy. But by then, the Sun will have expanded into a red giant, and Earth will have long been swallowed. In 100 billion years, all other galaxies will have disappeared from our view due to the expansion of the universe, and astronomers will then believe that the Milky Way is the entire universe. In 1 trillion years, the last star will die, and the universe will once again enter eternal darkness. Further on the order of 10 superscript 3 years, even atoms will be torn apart by expansion, and protons and quarks will disintegrate. Ultimately, only uniform heat energy will remain. This is heat death. Of course, it may not be heat death. Perhaps the universe will expand to a certain point and then contract, shrinking back to a singularity, and then explode again. If this is the case, then our universe may already be in its 335th cycle. The physical laws of each cycle may be different. Some may be five-dimensional space-time, and some may not have stars at all. Returning to the large ring mentioned at the beginning, it's very close to the giant arc discovered in 2021, suggesting they may belong to a larger structure. They seem to remind us that perhaps 13.8 billion years is merely the limit of what humanity can currently observe, not the true beginning of the universe. The Hubble Space Telescope once pointed at a small, blank area of the sky, continuously exposing it for 10 days, capturing images of over 3,000 galaxies, only 1/24 millionth of the entire sky. The observable universe has a diameter of 93 billion light-years and contains over 7 trillion galaxies. But this is only the observable part. Beyond that, in places we can never see, the universe may have only just begun. So, how big is the universe? The answer is likely a little bigger than we thought yesterday.